Okay, guys, in this session, we are going to discuss the new concept called a virtual ground. So, this is a very important property of an operational amplifier, which is very much used in solving a closed loop problems. That is, Opamp, whenever it is operated in as an amplifier, this concept is very much used. Please try to understand it is a very important property. That's called an virtual ground. Now, please understand what do you mean by an virtual ground here. See, there is no any physical connection. There is no any physical connection between the 2 points. Between the 2 points. That's why the name called an virtual. But still the points are connected. Now please observe here. So the op-amp in open loop mode. The op-amp in open loop mode, we can write here it is. It's V plus and V minus, that is inverting and non-inverting terminal. The op-amp output is V out, V out. So what is the op-amp output we can write? The op-amp output here is, what is the op-amp output we can write? Or we can call this V plus is same as a voltage V1 and V minus say voltage is V2. So what is the output voltage we can write here? It is V out is equal to what? So we know the op-amp is what here? It is a differential amplifier. I can write it is AD into it is V1 minus V2, or we can just write it is same as I can just write it is a differential amplifier. It is AD into VD. So that is what is VD here. It is a difference of the input voltages. A difference of the input voltages, that is V plus minus V minus. From this equation, what we can write here, it is what is a VD we can write. A VD is equal to the output voltage V naught divided by a differential gain AD. So from this equation, now please observe here what we can write. Observe carefully. So we know the differential gain AD of an op-amp is very large, but ideally its value is infinity. Ideally its value is how much here? It is infinity. So what we can write here, it is from this VD is equal to we can write it is V naught divided by it is infinity, V naught divided by infinity, or you can write Vd is equal to V naught by infinity. What you can write? Something by infinity it is, you can write it is 0, or what is Vd here? Vd is the difference in input voltages, that is your V1 minus V2. V1 minus V2 is equal to 0. So what we can write from this, if V1 minus V2 is equal to 0, so we can write V1 is equal to V2 R. What is V1 here? It is voltage applied at a non-inverting terminal, that is V plus. And what is V2? Voltage applied at inverting terminal, it is V minus. So we can observe here. So from the virtual ground concept, what we can write here, it is the potential at inverting and non-inverting terminal. The potential at inverting and non-inverting terminals, they are equal. Observe here. So since even they are not connected physically, see there is no connection between inverting and non-inverting terminals. That is your a node point A and node point B. Even though if it is not connected physically, but still they have the equal potentials. VA is equal to VB. That's why it is called a virtual ground. That's why it is called a virtual ground. There is no physical connection. Even though there is no physical connection, the potentials at both the points they are equal. See, this concept is very much used in the closed loop mode analysis of an op-amp, that is mainly in op-amps under applications of amplifiers. So this concept is very much used. So please remember, so from the virtual ground concept, we can write a potential at inverting and non-inverting terminal. They are equal. They are equal. So this is what an virtual ground concept of an op-amp. So this virtual ground concept is very useful in the analysis of op-amp when it is under negative feedback. That is, when you use the op-amp under an amplifier applications. So this is very much used. So that's why. So now after this, now let us consider another question. See, this is another question they asked in the examination. Least the characteristics of op-amp. See, we have already come across the parameters of an op-amp. That is what some important parameters we have called as characteristics. Some characteristics, that is the characteristics of an ideal op-amp. See, I have listed the values of the parameters of an op-amp for on both an ideal case and the practical op-amps. So in a examinations, the many times they repeatedly asked this question: list the characteristics of an ideal op-amp. And what is op-amp? We already know op-amp is basically, it is a direct coupled multi-stage voltage amplifier with very high gain, very high input impedance and very low output impedance. Or in other way, you can say op-amp is an operational amplifier. It can able to perform a various arithmetic operations. So now, what are the characteristics of op-amp? When you look at the characteristics of op-amp here, so one by one I will take. See, first one here is what here? It is an infinite voltage gain. We know op-amp has a gain to be a very large. So ideal op-amp has a gain to be very large, that is infinity. It is infinity. See, this gain is corresponding to an open loop gain of an op-amp. That is op-amp under open loop, that is without any feedback. See, this is what an open loop configuration of an op-amp. Under this configuration, the gain is, it is AOL. Please understand, OL indicates it is an open loop. It is infinity. It is infinity. Infinity. So now when it comes to an input impedance, see, a closed loop, there is again closed loop gain. The closed loop gain means it is a op-amp under feedback connection. This concept I will tell you later. But when it comes under closed loop gain, the op-amp closed loop gain will be less compared to your open loop gain, so fine. So now when it comes to an input impedance, as we know, op-amp has a very high input impedance. Basically, ideally speaking, the op-amp has a infinite input impedance. That is what a infinite impedance. The op-amp, ideal op-amp does not draw any current inside, does not have draw any current inside the op-amp. Therefore, op-amp has very high input impedance. Ideally, it is infinity, but practically it is of very large. So now, then the op-amp has zero output impedance. The third characteristic is what here? It is op-amp as a zero output impedance. So what is that? Zero output impedance means op-amp ideally, it is the op-amp output voltage of ideal op-amp is independent of the current drawn. So what is the current drawn at the output of an op-amp? Here it is, ideally it should be zero. Why? Because op-amp as a zero output impedance. So fine. Again next, see, after this, see, op-amp should have an infinite bandwidth. Why op-amp should have infinite bandwidth? Because we want to be amplified. The op-amp should allow all the range of frequencies, all the ranges of frequencies. So ideally we want op-amp bandwidth to be an very large. Ideally it is infinity. Practically it is in the order of 10 power 6. 10 power 6 hertz. So now, and the common mode rejection ratio, that is what, whenever the input of both the inputs of an op-amp to be a common signal, that is to be a signal, can be a noise, that noise is eliminated at the output, that noise is eliminated at the output. So ideally value of common mode rejection ratio to be very large. Ideally it is infinity, ideally it is infinity. So practically it is the value of very large. So now again we want an infinite slew rate. Again, this is a frequency sensitive property, frequency sensitive property of an op-amp, that's a slew rate. Op-amp slew rate is indicates that how op-amp changes the sudden change in the input voltages, that is what your op-amp dv naught divided by dt, how your output voltage changes, where is a sudden change in the input voltages, that is what your dv naught by dt. So in ideally speaking, the op-amp should have infinite slew rate. Op-amp should have an infinite slew rate. That's what, there should not be any uh, time taken by op-amp for to react for a sudden change in the input voltage, sudden change in the input voltage. So now after that we have discussed this a zero offset voltage, zero offset voltage, that is what, whenever the op-amp connected both the inputs to be equal to zero, so ideally the op-amp output voltage also should be equal to zero. So in a next table, observe here, see, this is a table for comparison of all the characteristics, both ideal and practical values. You can use these values in the examination for writing the characteristics. Observe here, have written here. So this is what the table gives, a summary of the parameters of ideal and practical op-amp. The parameters of ideal and practical op-amp IC. So first parameter is, as I told, it is on voltage gain. Voltage gain for an ideal op-amp, it should be infinity, but practically op-amp, it should be very large value. Practically for an IC741, IC741, it's a value of 2 into 10 power 5. It's a gain value 2 into 10 power 5, 10 power 5. Next, input impedance, input impedance, input impedance of an op-amp. Ideally it is infinity, but practically it is of order 1 mega ohm. It is 10 power 6. It is 10 power 6. That indicates it is 1 mega ohm. 1 mega ohm. So now after that, the output impedance, what is an output impedance? Here it is ideally op-amp output impedance, it is 0, but practically it is very low. The low value indicates it is at 75 ohm, 75 ohm. Again, when it comes to bandwidth, ideal op-amp bandwidth to be very large. Ideally it is infinite, 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 practically of 1 megahertz. The bandwidth here, it is practical op-amp, it is 1 megahertz, means it can able to amplify a signal range of from 0 to 1 megahertz, signal to range from 0 to 1 megahertz. And it comes to CMRR, that is common mode rejection ratio. Ideal op-amp, it has a value infinity, but practical op-amp, it has a value 90 dB. This is in dB case. CMRR in dB. CMRR in dB. So that is what, a 20 a log of your differential gain to common mode gain. Common mode gain. So then when it comes to slew rate is a sudden change in output voltage divided by a sudden change in the input voltage. So ideally op-amp should have a infinite slew rate, but for a practical op-amp, it has a value 10 power 6. So you can, some textbooks they have written it is 10 power 6. We can also write this 10 power 6. 10 power 6 volt per second is also same as, please understand, I can take this 10 power 6 to denominator. I can write it is same as, I can write it is same as, it's volt divided by 10 power 6. If I take it denominator, I will get it is 10 power minus 6 seconds. You can write this 10 power minus 6 as same as It is 1 micro. Means you can write it in micro also. That is volt per divided by microsecond. Volt per microsecond. So that both are valid here. So again, input offset voltage. Input offset voltage, that should be 0 value. And for practical op-amp, it is a very less value. That is 6 millivolt. 6 millivolt. Again, power supply rejection ratio. So what is the power supply rejection ratio? Here it is power supply rejection ratio. It is ideally it is 0, but for a practical op amps it has a value. It has a value 10 30 microvolt. 30 microvolt per volt. 30 microvolt per volt. So again, input bias current. Input bias current. Ideally value of input bias current it is 0, but for practically as low as possible, the maximum bias current it is 500 nanoamperes. That is very small. And input offset current, that is a difference in the bias currents. So ideal value should be 0, but practically it is low. So the maximum value here it is at 200 nanoamperes. That is a difference in bias currents. So that is what this table gives the complete a characteristic summary of your practical and ideal op-amp. Practical and ideal op-amp. So this table is very much important. So please understand this. Yeah. See, after this, now let us consider the problem based on your common mode gain and even op-amp slew rate. Yeah, please observe here. So what is the given data from this question? So observe carefully. So now what he has given here is an op-amp as a slew rate. Op-amp as a slew rate. It is given here. It is slew rate is equal to 0.5 volt per microsecond. What is the maximum undistorted sine wave can be produced at a frequency? Yes, given it is a frequency. So we need to find out what is its an output voltage. What is its an output voltage? It is your Vm is question here. Or we can write what is the slew rate here. It is, we know slew rate here it is S is equal to a change in output voltage divided by a change in input with respect to time, change in output voltage divided by a change in time. So from this we know what is given. It is S value as given 0.5 volt divided by microsecond, or you can write it is same as zero point 0.5 into, if you take this micro, basically micro 1 micro it is 10 power minus 6, take it to a numerator, that becomes 0.5 into 10 power 6 volt per second. 10 power 6 volt per second. So what is the frequency value? Given it is a frequency value 6.631 kilohertz. So you can write a slew rate. From the derivation we got this expression slew rate. By using this equation we got this expression slew rate. Here it is what? S is equal to 2 pi f into Vm. So we can find out what is the maximum voltage of your signal. So we can write Vm is equal to S divided by 2 pi f, and what is the S value? It is 0.5 into 10 power 6 divided by 2 pi into, given it is frequency. Use this. If you simplify this, we get it is Vm is equal to 12 volts. So from this we can write the maximum undistorted sine wave. See, and he has given it is undistorted sine wave, means we can write this expression is same as Vm sine omega t. You can write a general expression is Vm sine omega t, or you can write this, it is equal to, what is Vm value? Vm value it is 12. Vm value it is 12 into a sine. We can split this. Omega is what here it is a 2 into f value. You can substitute. What is f value? It is 6.631 into 10 power 3t. See, this is what a undistorted output. It is an undistorted output. So fine. Again, what is the next question? You can observe the next bit here. It is, what is the maximum frequency of a sine wave? What is the maximum frequency of a sine wave that op-amp can produce at the output without distortion, given its peak value of the output voltage is 7. See, this is another way. So that is, in the first bit he has given the frequency and he has asked to find out the output peak voltage for undistorted case. Again here in the second bit he has given it is frequency, sorry, the peak voltage. We need to find out what is the undistorted frequency maximum we can achieve. So fine. So that is what here it is. Fm is the question mark here, the maximum frequency in which the signal is undistorted, and he has given the peak voltage. What is the peak voltage here? It is 7 volts, and the slew rate is remains same. We can write what is slew rate here. It is 0.5 into 10 power 6 volt per second. So from this equation, that is what a slew rate equation, S is equal to 2 pi f into Vm. We can solve for Fm. What is Fm is equal to S divided by 2 pi into Vm. So we can substitute S value and 2 pi into Vm value. So we can simplify for Fm. What is the Fm value we'll get here? It is 11.368 kilohertz. See, from these two bits you can observe here, if you are increasing F value, observe, if see the previous case, the F value we have used here, it is 6.63 kilohertz, 6.63 kilohertz. See, from this bit to this bit, observe here, the frequency is increased, but you can observe frequency is increased, but you can observe the voltage, the peak voltage here earlier it was 12 volt, and now this case the peak voltage got reduced. So that is what, whenever you want to increase, achieve a maximum frequency, in that case we need to compromise in the voltage level. We need to compromise in the voltage, output voltage level. So that is what, again another bit related to your common mode gain and the differential gain of an op amp. So observe what is given here. So what is given here? So determine. So the given here it is a determine the output voltage of an ideal op-amp. Sorry, it is given as an op-amp for an input voltage of 300 microvolt and 240 microvolt. Observe here they are given two voltages, that is one V1 and V2 is given. So what we need to find out? We need to find out its output voltage. The differential gain of an amplifier is 500, and the value of CMRR is given, it is 10 power 5. So please understand, whenever it is given it is CMRR. So that is, what is it? CMRR here it is a ratio of a differential gain to the common mode gain. Differential gain to the common mode gain. And he has also given a differential gain of an amplifier. It is your AD value is also given. AD value is also given. It is 5,000. Now please observe here. So what we can write the op-amp output. We know the op-amp output is, it is with respect to a differential gain and with respect to an common mode gain. So the generalized output of an op-amp, V out here it is, it is AD into VD, VD, VD plus AC into VC. See, this is a generalized output, but generally we will consider it is, most of the time we will consider it is a first term. It is AD into VD. Why? We are neglecting this AC into VC because the AC is very less value compared to your AD. So that is the case. So, but in this problem, we can see what is the value of AD and AC and what is the output contributed by your differential gain and the common mode gain. You can better understand from this example. So now please observe here. So this is what V out expression we have taken. So from this V out expression, so we know what is AD directly. It is given. It is 5,000 a differential gain. So we don't know what is AC here. We don't know what is AC. So first we need to find what is AC here. AC we can write. So from the definition of CMRR, what is CMRR is? CMRR is, it is a ratio of a differential gain to the common mode gain, that is AC. So from this we can write AC is equal to ED into, sorry, AD divided by your CMRR. Please observe here, AD divided by CMRR, it is 5000 divided by 10 power 5 or 5 divided by 100. You can write it is 0.05. Observe here, what is the value of 0.05? Just observe 0.05 and your AD is 5000. How far this two are differ? So now again you can find out what is VD. VD is a difference input voltages. You can write VD is equal to V plus minus V minus, or you can write it is V1 minus V2. You can write it is 300 micro minus 240. 240 micro, we will get it is 60 microvolt. And what is the value of VC? VC is a common mode voltages. That's a common mode voltages means it is an average of both the inputs. Average of both the inputs, that is V1 plus V2 divided by 2. V1 plus V2 divided by 2. So we can write it is 300 micro plus 240 microvolt divided by 2. So from this equation we will get it is, when you simplify this, both we will get it is 540 by 2, that is 270 microvolt. So when you substitute these values, you just observe here what you will get. Your V out is equal to ADVD ACVC. So you can write it is 5000 into 60 microvolt, and AC value is how much? We got it is 0.05, 0.05 into 270 into 270. You can observe here. See the result from this. The result from this, it is, please observe. So we will get it is, one is the from the first term. See from the first term, the result when you simplify this, we will get here it is 300 millivolt, 300 millivolt plus plus the second term. When you simplify this two, we'll get a result of, please understand here, it is 0.135, 0.135 millivolt. Please observe here, you can compare these two. Where is 300 millivolt and where is 0.135 millivolt? So that's why I told this term gives a maximum value compared to your AC into VC. That's why usually when you solve the problems, you'll neglecting your ACVC term. You're neglecting ACVC term. So the combined output V out, it is 300.0135 millivolt. So generally that's why AC value it is very very less. AC value it is very very less. So that's why the output contributed by this term, it is very less, that can be ignored when you compare to your AD into VD. So you can still make this AC value to be nearly approaching to zero by increasing a CMRR value. You can observe here CMRR. When you increase the CMRR, you can decrease AC very much low. So ideally, when you say CMRR, it is infinity. So you can say AC value is, ideally it will be zero, but practically it is very less value. Practically it is very less value. So that is what about that. Yeah, yeah, yeah. Next, so there is an very important concept. There's a question. Explain. You can just read this question first here, then we can answer it later. Just understand the first question here. So very important concept of an op-amp, that is a closed loop concept of an op-amp. So first you understand the question. Why Opamp? Why Opamp? Read the question here. Why Opamp? Observe here. Explain why a closed loop configuration. Please understand here. Explain why a closed loop configuration of Opamp is used in all practical amplifier circuit. Most of the time we will go with an closed loop configuration instead of an open loop configuration. That's the reason why is asking. And bring out the advantage of closed loop operation with a negative feedback. So there's another question is, explain what are the advantage of using a closed loop operation. So now please understand what do you mean by a closed loop. See, in earlier cases we have come across till now, it's an open loop operation. See, this is what an op-amp under open loop, op-amp under open loop mode. This is op-amp under open loop mode. And whenever we use a feedback resistance from your output to the input, observe here, there's a feedback connection from output to the input. Either you can use it at a negative terminal. So this is what it becomes a negative feedback. If at all, if you are using output from a positive terminal, that becomes a positive feedback. So most of the time we are using op-amp under negative feedback connection. So that is what a feedback resistance. RF indicates it is a feedback resistance. It is a connected from output to the input. The reason why the op-amp is preferred in a closed loop configuration instead of an open loop configuration. So very important question here. So please try to understand what is the reason behind why we are using op-amp under closed loop configuration instead of a open loop configuration. See, answer for this question, observe here. When you look at this open loop connection, what is a V out? So generally the expression V out here, it is what? It is AOL into V1 minus V2. AOL into V1 minus V2. Observe here. So from this expression, you can look at here. What is the gain value? Gain value, open loop gain value, ideally it is infinity, but practically it has a value of 10 power 6. I can say it is 10 power 6. Now, whatever you give a input voltages V1 and V2, the maximum gain that can be achieved here, it is a 10 power 6. It is 10 power 6. Say it is a 10 power 6. Suppose if at all I want to use, say for example, I don't want a gain of 10 power 6, say consider I want to use a gain, say for example, I want a gain of say 100, or say gain of I want 100, or a gain of 1,000, or a gain of say for example I want a gain of say 500 or a 5,000. See these values which is less than to a practical case. What is a maximum practically achievable gain here? It is 10 power 6, but these values are less compared to your practically achievable cases. So is it possible to implement a gain with a 100 or a gain with 1,000 or a gain with a 500 in an open loop mode configuration? See, in an open loop mode configuration, whatever you give a input voltages V1 and V2, so that will be amplified with a gain of 10 power 6. Gain of 10 power 6. Of course, there is a limitation of output voltage also that I will come to later. So, but ultimately gain will be what here? It is 10 power 6. That is fixed. So there is no gain control. So that is a one drawback in open loop mode. So suppose if at all I want a gain value of 100 or 1,000 or 5,000, that you cannot implement it in open loop configuration. So that is another drawback here. It is no gain control. There is no gain control. You cannot have a op-amp under a gain of 500 or 1,000 or a 5,000 under open loop mode. So there is no gain control. In a gain of an open loop, it is 10 power 6, that is fixed. You cannot vary, you cannot design your own gain under open loop configuration. So that's why we're moving to a closed loop configuration. See, this problem is eliminated in closed loop configuration. The second very important drawback of your open loop configuration is, see, we know what is an output voltage. Observe here, what is output voltage here? It is AD into VD. Say what is your VD? We can write VD is equal to, we can write it is how much here? It is V out divided by, under open loop, what you can write? It is V out divided by AD, V out divided by AD. Now please understand here, the maximum achievable output of your op-amp is plus or minus its saturation voltage. that I will come to later when we discuss the saturation property of an op-amp, divided by it is AD. Observe here. But practically, what is the value we can write? See, plus or minus which saturations are nothing but your supply voltages. It is VCC or VEE. For a practical op-amps, it is a 90% of your supply voltages. I'll just consider it is a 12 volt, plus or minus 12 volt. And what is the value of AD? So for a practical op-amp, a differential gain, it is 10 power 6, 10 power 6. You can write it is plus or minus 12 into 10 power minus 6. I can write it is. Now observe here. In order to use a op-amp under open loop mode configuration, we need to maintain this difference in voltage should be a 12 microsecond. 12 microsecond. This is very negligible voltage. See, even most of the CROs are not recognize this micro voltage levels. So it is very difficult to handle this input voltages under micro volt level. So this is another drawback. So in order to avoid these drawbacks, we will use op-amp under closed loop mode. Okay, guys, I will be stopping here. So I'll be continuing in the next session. Okay, fine. Thank you.